In this lesson, we will be covering speed warnings. Included in this will be overspeed and stall warnings. The purpose of the overspeed warning system is to alert the flight crew if the airspeed exceeds the VMO, MMO limits calculated by the air data computer, where VMO is the maximum indicated airspeed and MMO is the maximum Mach number. When we enter an overspeed situation with an electronic system, the following events occur. A clacker is sounded, and the red master warning lights illuminate, and the overspeed message is displayed on the ICAS upper display. The warning cannot be cancelled by pressing the red master warning light and will continue until the crew slows the aeroplane. The overspeed warning light obtains its input from the air data computers via the flight warning system. It has a test facility which can only be used on the ground and checks the oral warning. In the event of system failure, the crew receive no warning if the maximum speed is exceeded. The maximum allowable airspeed is shown either on the airspeed indicator by means of a barber's pole or on an airspeed tape on the primary flight display. Initially, during the climb, VMO is the limiting speed and is indicated by the barber's pole. As the aeroplane climbs from 24,000 to 29,000 feet, then MMO becomes the limiting factor, and this is manifested by the barber's pole reducing in value. The reason it does this is that as altitude increases, when climbing at a constant indicated airspeed, MMO, when expressed as an indicated airspeed, decreases. We will now look at the opposite end of the speed scale and the stall warning system. The purpose of the stall warning system is to warn the crew of an impending stall. It does so when the aircraft approaches the stalling angle of attack, dependent on the current speed and configuration of the aircraft. The simplest system consists of a hinged vane-type sensor positioned on the leading edge of the wing and protruding into the airflow. This sort of system is fitted to several types of small aeroplane. In normal level flight, the airflow maintains the vane in line with the relative airflow. As the angle of attack increases, the airflow meets the leading edge at an ever-increasing angle and causes the vane to be deflected. When this deflection reaches a preset value, a switch is made and an oral warning is sounded. Regulations stipulate that in large aeroplanes, the stall warning system must activate before the stall speed by an amount greater than either 5 knots or 5% of calibrated airspeed. It must continue to work until the angle of attack is reduced to at least the point where the stall warning was initiated. The warnings can be in the form of visual warnings, sensory warnings, such as stick shakers, which are fitted to the majority of traditional type aeroplanes, and audible warnings.
Stall, stall, stall.
Most aeroplanes tend to use a combination of these indications, and more modern aeroplanes use the visual and audio indications as their stall warning system.
Stall, stall, stall.
We now move on to the stall protection system. The basic difference between this and the stall warning system is that at the onset of stall protection, providing it has not been isolated, it cannot be overridden, whereas a stall warning system can be. In traditional aeroplanes, stall protection takes the form of a stick push, which physically moves the control column forward, initiating a reduction in the angle of attack. If we look at this graph for a typical fly-by-wire aeroplane, its protection starts at alpha protection, where alpha is the angle of attack. At this point, even if the pilot is demanding full-up elevator, the system will only provide a proportion of the actual demand. As alpha continues to increase and reaches alpha floor, the thrust levers are selected to take-off go-around thrust to safeguard the aeroplane. We are now going to look at the typical components required for a stall warning protection system to function. If we look at the inputs required, we need to know the angle of attack, which is provided by a sensor, which we will be looking at in more detail in the next part of this lesson. The positions of flaps and slats affect the pitch of the aeroplane, and therefore the system requires that information. Airspeed is another requirement, and is supplied from the air data computer. The amount of power on the aircraft is also a factor, as the power on stall speed is higher than the power off stall speed. The stall warning system is inhibited on the ground, and so we need an input from the weight on wheels microswitch. We will now look at the outputs from the stall warning module, and as already stated, aeroplanes will have a combination of indications. First is the stick shaker motor, which is fitted to more traditional aeroplanes. Then we have visual warnings, which come as master warning lights, and written warnings on electronic screens, and audible warnings in the form of synthetic voices and oral warnings. We also have an output to the angle of attack indicator. There is also a test facility, which can only be used on the ground to test the system. A stall protection system differs from the stall warning system only in that it is triggered at a later stage than the stall warning, and it has different outputs. In a traditional aeroplane, we have the stick push, whereas in more modern aeroplanes, we have an output to the auto throttles, which move them to take-off go-around thrust. As previously mentioned during the components phase, we are now going to learn about the angle of attack sensing probes. They are positioned on each side of the forward fuselage with two basic types in use: a vane type or a conical slotted probe. Both are protected against ice formation by a heater. The vane detector is a counterbalanced aerodynamic vane, which positions the rotor of a synchro, which is used to measure the subsequent angle. The conical probe protrudes from the side of the aircraft into the airflow. The probe is attached to a paddle wheel inside the transmitter housing, and has two vents set into it, which feed either side of the paddle wheel. As the aeroplane rotates, the airflow strikes the probe differently, and this causes a pressure differential within the paddle. The paddle and probe then move so as to rebalance the pressure. The probe, or vane, drives an electric pickup, which is then sent to the stall warning module, and can be displayed on an angle of attack indicator if fitted. During this lesson, you have learnt about high-speed and low-speed aerodynamic warnings. The first thing to be looked at was the overspeed warning and the indication provided to crews. Then you were shown the stall warning system and the different ways this is indicated to a crew dependent on how modern an aeroplane you are operating. Next was the stall protection system, how it differs from stall warning, and the different ways it is presented to the crew dependent on the age of the aeroplane. Finally, we considered the components of a typical stall warning system, including the types of probes that are used to input the angle of attack to the stall warning protection system.